Mathematical induction is a form of proofs, and there's specific steps for it that you have to follow every time. So if you have a proposition, we'll call it P of n, if its proposition is true if you have two things that happen. The first thing you do is you show that P of 1 with the first thing is true. This is called the anchor. The next thing you look at is you assume that P of k is true, so that would be your inductive hypothesis. And then, because this is true, you show that that means that it's true for the next term, P of k plus 1. Yes, we use these in sequences and series so that because we're looking at one term after another and seeing if something's true. This is the inductive step. So what we're saying is if we start and the first one's true, and then that we prove that for every term, if it's true for that term, then it's automatically true for the next term, then we've proved the whole thing. Now, logically, that makes a lot of sense, because if we show that the first one's true, and if we show that because the first one's true, that means the second one's true, which means the third one's true, which means the fourth one's true, and so on and so forth, then we've proved the whole thing. So let's do an example. Let's say we want to prove that we have this series here. Oops, that should be a plus sign. Then we can add it all in one little step like this. So what we're saying is if we have this sequence that we're adding it all up, so a series of numbers, and we add it all up, then we could boil it down to just this one simple little formula. So we would, if we just knew how many terms we were looking at, then we'd have this automatically. So let's prove this by induction. So the first thing we look at is the anchor. We need to look at the first term. So we look at the first term and we say, well, the first term on the left-hand side is 1 times 2, and we want to know if that's equal to, if we plug in n equals 1, so we simplify this, we have 1 times 2 times 3 over 3, those cancel, and we get 2, so we have that 2 equals 2. So we've proven that the anchor is true, that P of 1 is true. The next thing we do is we look at the inductive hypothesis. So the inductive hypothesis is P of k. So what we're going to do is we're going to actually write this out. And we just put in k for n because we're looking at the kth term. And I know it seems a little bit silly just to change the letter, but it actually is part of the step-by-step process. So we write our inductive hypothesis, which means that it's true for the kth term. And yes, you write out the kth term part, and then you write is true. Now, the next thing we're going to do is the inductive step. So we take this and we add the next term. So we start out with our P of k, and we're just going to insert in the next term here. And when you add one thing to one side, if you want to keep an equation the same, you have to add the same thing to the other side. So our next term is going to be k plus 1 times k plus 1 plus 1, right? That's our next term in this series. So we're going to have to add that to both sides here. So we need to see if this is true. So we have 1 times 2 plus 2 times 3 plus dot 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 plus k times k plus 1, and then we add that next term, so k plus 1, and I'm going to go ahead and simplify it to k plus 2. And we want to know, we know that it is equal to this plus, and then we have that k plus 1 times k plus 2 term here. So we have all we did was add the same thing to both sides. So we know that's true. It always is true. Every mathematical time we've ever done anything, if you add the same thing to both sides, you still have an equation. So what we're going to do is simplify all this stuff down now. What do you do with your fractions? That's right, you get a common denominator. So I'm going to come over here so I have some room. So I've got k times k plus 1 times k plus 2 over 3. My common denominator is obviously 3. So that means I'm going to have to multiply this times 3 over 3. Now, if you add this together, you see you have a common term in both of these. So we have k plus 1 times k plus 2, and then times k plus 3, because we have a k left over here and a 3 left over here. And then, of course, we're still all over 3. Now, if you look at this, this is the statement for p of k plus 1, because what's our statement for p of k plus 1? Well, for this to be true for k plus 1, we'd have k plus 1 times k plus 1 plus 1 times k plus 1 plus 2 all over 3, which would be k plus 1 times k plus 2 times k plus 3 all over 3. So what you would say then is, this is the statement for p of k plus 1. So p of n is true for every integer by mathematical induction. Kind of ran out of room there, sorry. Okay, so mathematical induction. Once you get to the point where you've simplified this down and you get what you would have gotten if you plugged in k plus 1 to the original thing, then you've proven it. So how do we do this? Well, we start with our what we're trying to prove. Then you show that the anchor is true. So p of 1, show that that's true. Then you write down your inductive hypothesis, which is the p of k term. So you just plug in k and you write that it is true. Then you add the k plus 1 term to both sides. So whatever would be next on this in this series for the k plus 1 term, you add that same thing to both sides. Then you simplify the right-hand side and show that it would be the same thing as if we did a k plus 1 term in the original thing we're trying to prove, in the original proposition. So, and after that you would write this is the statement for p of k plus 1. So p of n is true for every, that upside down a means for every integer by mathematical induction. So that's all there is for induction. It'll take some practice, so make sure you try several problems.